So, we had just completed conservation of mass and momentum. Just let us quickly take a recap of what we had derived. So, you can see that we had derived the conservation of the mass either as this form or this form. We did use this form in the conservation of momentum. We took the conservation of momentum, applied RTT, that is the Reynolds transport theorem, and we derived the surface forces and the body forces in the differential form, and got the Cauchy's equation and substituted the stresses in terms of the velocity gradients and the viscosity, and we got this equation. So, if you write the complete equations, so what is that you have gotten here is that the conservation of mass, that is continuity equation, is d rho by dt plus rho of del dot v equal to 0. This is continuity equation. Now, the x momentum equation is that rho du by dt is equal to minus of dou p by dou x plus mu into del squared u by del x squared plus del squared u by del y squared plus del squared u by del z squared plus del by del x of mu by 3 into del dot v plus f of x. Similar, this is x momentum equation. Similarly, y momentum equation is rho dv by dt equal to minus dou p by dou y plus mu into dou squared v by dou x squared plus dou squared v by dou y squared plus dou squared v by dou z squared plus dou by dou y of mu by 3 del dot v plus fy. This is y momentum equation. Similarly, x momentum equation is rho dw by dt is equal to minus dou p by dou z plus mu into dou squared w by dou x squared plus dou squared w by dou y squared plus dou squared w by dou z squared plus dou by dou z of mu by 3 dou del dot v plus fz. So, you have 4 equations, and the 4 unknowns. The 4 unknowns are, which you are going to solve, is P, U, V, W. So, you get the complete pressure distribution and the velocity distribution if you solve this equations. So, this is, that means it is mathematically well posed. That means number of the equations are equal to the number of unknowns, mathematically well posed. It is a non-linear, it is, unfortunately it is not possible to solve except few simplifying cases, simple cases, non-linear second order differential equation this is. And this was first derived by Navier and Stokes parallelly. Navier and Stokes parallelly derived these equations. So, that is why this is called Navier-Stokes equation. Navier is French mathematician and Stokes is a English, he is from England, English mechanician, that is fluid mechanician. Okay, they independently derived them. So, now if you just see this, each of these terms, actually the first term, this is what is called as the inertia term. This is mass into acceleration. So, that is why this is inertia term. This is because of the pressure force, and this are because of the viscous forces. This is because of the viscous forces, because by virtue of viscosity, okay, and this is body force. So this is the physical significance of each of these terms. So you should remember that this is inertia force, this is mass into acceleration, this is the pressure force term, and this is viscous force, and this is the body force term. Okay. So having understood this, actually if you remove the viscous term, this equation should reduce to Bernoulli's equation. Does that happen? Yes, it does happen. So if you see that, if you just see, so this is, you can write this in the, you can write this actually in the vectorial form, that is here. I am not going to write that here. Rho dV by dt, you can combine all of this, you can write that rho dV by dt equal to minus del P mu del squared V plus mu by 3 del of del dot V plus F. So if viscous term is 0, so you have constant viscosity, you can write this as mu of del dot V, and if viscosity is 0, then what will happen? If it is for incompressible fluids, del dot V is 0, so this term gets cancelled out, and that is what we have written here. Now, okay, we will write this. So if we write this, so what is that I get here is that I get in the vectorial form as rho dV by dt is equal to minus del P plus mu del squared V plus mu by 3 del of del dot V. This is for viscous, compressible, constant viscosity fluids. But if it is incompressible viscosity, if it is incompressible, we know that for incompressible fluids, we know that del dot V is equal to 0. So you get rho dV by dt is equal to minus del P plus mu del squared V. This is for incompressible fluids with constant viscosity. Now if you take inviscid means ideal fluid where there is no viscosity, viscosity is 0. So that is rho dV by dt equal to minus of del P. This is nothing but my Euler's equation, which can be reduced to Bernoulli's equation, which is P by rho plus U squared by 2 plus Gz equal to constant for along a streamline. So that I am not going to do, but I will just show you the steps which are involved in that. So you just take the Euler's equation, take a streamline, okay, which is of length delta S, consider steady incompressible inviscid fluid. So then that means you have whole of this total derivative reduces to rho dou U by dou S because it is steady. So dou U by dou T is 0, and you have dou P by dou S along a streamline. F is the body force because of the gravity that is acting along the streamline, that is minus rho G sin theta. So if you write this sin theta as dou Z by dou S, so if you integrate this equation, so you get P by rho plus U squared by 2 plus Gz equal to constant, which is nothing but my Bernoulli's equation which we have studied in fluid mechanics. So that's how we have completed the momentum equation derivation. So the next logical thing after conservation of mass and momentum is conservation of energy. So we shall do the conservation of the energy in Cartesian coordinates. So for that we need to take the recourse of first law of thermodynamics. So let us get started with first law of conservation of energy. So, for that, from first law of thermodynamics, you have dE equal to dQ plus dW. If you take the total derivative, you get dE by dt equal to dQ by dt plus dW by dt. Or what is dE? dE is increment in kinetic energy plus thermal energy of the system. Kinetic energy plus thermal energy of the system. Okay, and dQ is heat transferred to the system. Heat transferred to the system. Now, dW is work done on the system. This we have studied in thermodynamics, that is why I am stating it directly. Now, kinetic energy is u squared plus v squared by 2. I am doing 2D because 3D becomes very clumsy, but we can extend this to 3D little later. And the internal energy, that is the thermal energy, is nothing, thermal internal energy, that is represented by E. So, now let us try to apply the Reynolds transport theorem for conservation of energy, RTT, Reynolds transport theorem, that is dB system divided by dt is equal to dou by dou t of rho b dV for control volume plus rho bv dot n dA across the control surface CS. Now, B is E, that is internal energy, thermal internal energy E plus kinetic energy u squared plus v squared by 2. So, B equal to mB. So, if you apply this, so what is that you get is the rate of increase of E in CV, that is this term, minus rate at which E enters through the surface of control volume plus rate at which E leaves through the surface of control volume. That means these two terms correspond to this. This should be equal to I have written already dE by dt equal to dQ by dt plus dW by dt. So, this which are acting on the control volume, that is rate of heat transfer into control volume by conduction plus rate of surface. Who is doing the work here? This is this term. The rate of surface and body forces, doing the work. So, each of this block now we need to expand that in the differential form. That is the next effort what we are going to doing the work on control volume. That is what we are going to represent now. So, let us take up first the left hand side. So, if I take the left hand side, that is the rate of increase in the CV, rate at which it enters and the rate at which the E leaves the control volume. So, I take the control volume, a simple parallelepiped, okay, and you put that here. So, you have delta x, delta y, delta z. So, what is entering is rho E, it is entering with a velocity u, delta y, delta z. E u, the energy which is entering is rho E u delta y delta z. This is this term, the rate at which this term is what I am writing. Okay, rate at which the E enters through the surface, that is that. And what is it? It is leaving rho E u delta y delta z plus dou rho E u by dou x delta y delta z. And what about this? This is rho E v delta x delta z, then rho E v delta x delta z plus dou of rho E v delta x delta y delta z. Rho E v dou y delta x delta z. Okay. So, this will become, this is negative because this is entering. So, these two terms are negative and these two terms are positive. So, that means this term gets cancelled out with this term and this term gets cancelled out with this term. So, on the left hand side I am left out with that, that is control volume rho E v dot n dA. Remember this is what we are trying to write. If you this term is what we are trying to write. So, that is why if you have rho E v dot n, so that is why you have E into flow rate, that is rho into u into delta v delta z, that is what it happened. So, you are left with dou of rho E u by dou x plus dou rho E v by dou y into delta x delta y delta z. And another term which is control surface, this is control surface. So, dou by dou t across control volume rho E dx dy dz, that is dou of rho E by dou t delta x delta y delta z. So, whole of the left hand side, if you write the left hand side divided by delta x delta y delta z is dou of rho E by dou t plus dou of rho E u by dou x plus dou of rho E v by dou y. Okay. So, now we need to expand this. So, we will expand this. So, that is dou of rho E by dou T plus dou of rho EU by dou Y plus dou of rho EV by, sorry, this is X by dou Y is equal to LHS divided by delta X, delta Y, delta Z. Now let us expand this. I will keep first rho constant and then E constant. So you have rho dou E by dou T plus E dou rho by dou T plus, take out rho U as rho U into E you can write. So you can write this as rho U dou E by dou X plus E dou rho U by dou X plus rho V, here you take rho V and E. So rho V dou E by dou Y plus E into dou rho V by dou Y. This is equal to LHS by delta X, delta Y, delta Z. So now what you can do is you can just take rho as constant here, rho into dou E by dou T plus U into dou E by dou X plus V into dou E by dou Y plus E into dou rho by dou T plus dou rho U by dou X plus dou rho U V by dou Y is equal to LHS divided by delta X, delta Y, delta Z. Now you see what happens. So this is nothing but the total derivative dE by dt. So you have rho dE by dt and this is continuity equation. That means the continuity equation, this becomes 0 by conservation of mass, conservation of mass. So you get rho dE by dt equal to LHS divided by delta X, delta Y, delta Z. This means is also equal to d by dt of capital E is nothing but E plus U squared plus V squared by 2. Okay. Now let us keep this like this for a minute and get to the other terms, that is the rate of heat transfer into control volume by conduction. So let us take up that term. So the rate of the heat transfer by conduction, rate of heat transfer by conduction. Okay. So you again take a parallelepiped like what you did in the heat diffusion equation. If you recall, you had done this in heat diffusion equation while we derived for heat diffusion equation, which Professor Arun did. So you have delta X, delta Y, delta Z. So you have the conduction which is taking place, that is Qx dot into delta Y delta dy, you can even write dy dz, dy dz and Qx dot dy dz plus dou Qx dot divided by dou x into dx dy dz. Similarly, the heat transfer in the y direction, Qy dot into dx dz into another term Qy dot dx dz plus dou Qy dot divided by dou y into dy dx dz. So the negative sign is heat transfer is arises because the heat transfer is counted, this is heat added. Heat added is considered as positive. This is positive term because the heat added, this is heat lost from the control volume. So, this will be positive and this will become negative. This will become negative. So, in that case, this term and this term get cancelled out, and this term and this term get cancelled out. So, you will be left with dou qx dot. So, dou qx dot by dou x in the negative sign plus dou qy dot by dou y, both are negative. Okay. So, this is into dx dy dz. Now, qx dot, by Fourier's law of conduction, the qx dot can be written as minus k dou t by dou x plus dou by dou y of minus k dou t by dou y into dx dy dz. So, minus into minus, if you just push this and pull out k, k is constant. If you assume that k is uniform, here in this case it is not constant. Constant term is used with reference to time, with reference to space you use the term uniform. In that case, this equation reduces to k into del squared t divided by del x squared plus del squared t by del y squared into dx dy dz, dx dy dz. So, that is about the rate of the heat transfer by conduction. Now, let us try to do the rate of heat transfer, rate of work done, rate of work done, rate of work done by pressure force, rate of work done by pressure force. So, to do this, so let us draw parallelepiped which is having delta x, delta y, delta z. So, you have work means force into velocity. Force acting here, pressure always acts inwards. So, P into delta y delta z, this is the pressure into area gives me the force. This into velocity u, x direction velocity gives me the work done. So, here it is pressure is acting inwards. So, u into P into dy dz plus dou of up by dou x into dx dy dz. This is the at the other side. Now, here again P into dx dz is the force into velocity, velocity is v in the y direction, and here this is vp dx dz plus dou of vp by dou y into dy dx dz. So, how to take them as positive, negative, all that we shall try to understand in the next class and continue this derivation, so that we will achieve the energy equation and try to see the temperature in our energy equation. Thank you.